welcome again. We are going to continue on by looking at our Unit 2 notes. So for today's class, we're essentially going to identify what it means to have like terms and then to combine them by looking at their coefficients. So this should feel pretty straightforward, at least at first. Later on in, thank you, Hannah. Later on in Unit 2, we're going to start solving equations, linear equations, which could potentially bring about some frustration. So we'll get there, and I want to show you essentially all the different things that you can do, are allowed to do within this math context. Okay, let's take a look at our notes. Combining like terms. In this section, we will learn how to simplify expressions. So when we hear the phrase like terms, I want you to think of terms with the same variable or variables. Like a term can have multiple variables, right? So for instance, if we have something like a 10x or a 3xy, those are each terms with their own sets of variables. But in addition to the terms having to have the same variables in order to be like, they must have the variables to the same power. So terms with the same variables or variables to the same power. Or powers, of course, if there are multiple variables. Or terms that have no variable. A term that has no variable is called a constant. Think of it as never changing. Variable vary. It varies. It changes. Hi, Ashanti. Think of a constant. Is a constant value. It is unchanging. Hopefully that's clear. So let's take a look at identifying the number of terms. Notice here I created a little note for you, and that is that terms are generally separated by addition or subtraction signs. That's very important to think about and to kind of digest. Terms are generally separated by addition or subtraction signs. Okay, we're going to look at our first example here. So we can determine the number of terms and then identify our variable and our constant terms, if we have any, of course. So our first example is a negative 13m plus 12. Notice here my first term is a negative 13m. My second term is a positive 12. And I know that these are two terms because they're separated by addition. So I'm going to say here for number of terms, 2. Next, the variable term. The variable term is the term with an actual variable, a letter, something that can have any sort of value replaced inside of it, right? Or replaced or substituted. So we have our negative 13m as our variable term. And for our constant term, we have 12. There is no variable associated with that 12, so it's constant. It is never changing. Good. Simple enough, right? Okay. Take a look at the second example. We have 4 times 2p plus 5 minus 9p plus 2. As you look at this particular problem, you may think to yourselves, okay, well, how many terms do I have? Is it 1, 2, 3, 4 because it's separated by addition and subtraction? Is it 1 and 2? Is it... Oh, good. We have some guesses in the chat. And I'm very excited about these guesses because it means that you're trying to dissect exactly what this looks like. Now, believe it or not, this particular expression has, drum roll please, 3 terms. This has 3 terms because remember, terms are generally separated by addition or subtraction signs. Now let me reread this. This says 4 times 2p plus 5 minus 9p plus 2. So as crazy as that might seem to you all, you're like, what? How is it just 3 terms? Think of this as 4 times a quantity. That quantity can really be represented by a variable of our choice. So for instance, let's say I wanted to get fancy with it. Let's say that I wanted to call the letter A 2p plus 5. If I wanted to call capital A 2p plus 5, that means my expression can actually be rewritten as 4a minus 9p plus 2. Yes, perfect. So now you can see more definitively that, wait a second, okay, this is definitely 3 terms. It's 4 times a quantity and then minus 9p plus 2. So your variable terms are going to be your first 2 terms here. So your first term is 4 times 2p plus 5. That's your first term. Your second term is a negative 9p. The sign has to go with the term. The sign directly in front belongs to that term. Your constant term is a positive 2. I don't write the plus in front, but you can if you would like to. Generally speaking, a value is positive unless otherwise noted with a negative sign. Now, to take this just a tiny bit further and to show you without a shadow of a doubt how this is 3 terms and not more than that, I'm going to rewrite our expression here, 4 times 2p plus 5 minus 9p plus 2. What we could do is we can actually open this up. Once we open it up, then we can count the number of terms that we have. So notice my coefficient of 4, okay? This coefficient is directly in front of this set of parentheses, so the 4 is going to be distributed into this set of parentheses. Think of this as you start here and you end here. Distribute the 4, start, end. So we're going to distribute to each term. So we have 4 times 2p, which is 8p, and then 4 times positive 5, which is positive 20. I'm going to write down the rest of the terms, and voila. Now we see, okay, I've just opened this up, so now I have 4 terms. I can clean this up and combine like terms, but that's not the purpose of this exercise right now. I simply want you to see that after distributing, now I have my 4 terms. Excellent. Like terms are combined by adding or subtracting their coefficients. Their coefficients are essentially the numeric part of a term, right? So when we had negative 13m up here, negative 13 was the coefficient. When we have, for instance, 4a over here, my coefficient is 4. When we have the negative 9p over here, my coefficient is negative 9. So we can see what the coefficients are, no problem. Taking a look at this first example, we have 11 times 4x plus y minus 3x plus 15. We have 3 terms. What we'd like to do is always distribute to drop parentheses. And I'm going to make that a note, although I'm sure I've written it somewhere else in our notes. I'm just going to put a note here, distribute to drop parentheses. Okay, distribute to drop. You like that alliteration? Distribute to drop parentheses. So what we're going to do is we're going to distribute the 11 to both terms. That will give us 44x plus 11y minus 3x plus 15. Once I have distributed to drop that set of parentheses, I can now combine like terms. Remember, like terms are terms that have the same variable to the same power. So right away, notice that 44x and a negative 3x, these are my like terms. So 44x take away 3x will give me 41x. Notice that we have an 11y and a 15. We do not have another term with y, so we simply write that next, 11y. And we don't have another constant to combine with the 15, so we simply bring the 15 down and we're done. That's all there is to it. Distribute to drop parentheses, combine like terms. Let's do it again. This time, for each of our problems, I would actually like us to indicate what that operation is. We're going to write the operation in this block, okay? And then we're going to do the math here. So for number 1, I have 2x plus 3y minus 7 plus negative 13x minus y plus 11. Notice for this particular problem, the indicated operation is addition. So I'm going to write addition in our box here. I will tell you that I want you to consider identifying the operations first. Every time you see these kinds of problems, especially when we get into the more complicated things later on in the semester, it's going to be really important for you to say, okay, what is the operation I am seeing? That's what I'm going to do. I have seen students later in the semester see a problem like this and start to distribute, meaning they would start to distribute 2x times negative 13x, 2x times a negative y, 2x times 11, and they're multiplying these two parentheses together, which is nutty to me because there's a big old plus sign in the middle. So as simple as that might sound, please be careful. Take a step back, be critical. What am I actually doing here? Oh, I'm adding, okay, which means I'm dropping the parentheses by distributing a positive 1 or a negative 1, whatever I see here, and then combining like terms. So let me show you the proper procedure for these. Notice that in front of this set of parentheses, we don't have a coefficient written. We know that the coefficient here would be 1 whenever we don't actually see it. There's lots of imaginary ones here, right? There's a lot of instances where we see this. So what we want to do is essentially drop the parentheses by distributing a positive 1. If we distribute a positive 1, notice that none of the terms within the set of parentheses will actually change. So we have a 2x plus 3y minus 7. And then we have a positive and negative 13x, so it's minus 13x, a positive and negative y, which is in minus y, and a positive 11, which is positive 11. Notice that even when we distribute a positive sign or a positive 1, we're not changing the terms either. Now, Claire and Hannah, you both recommended that maybe we put boxes or circles or anything like that to kind of help us to identify what it is that we're doing. So what we may want to do is to identify the terms that we're combining. So we're going to start with the 2x, and we're going to combine it with the negative 13x. You see how I've kind of identified that those two are the same. Nice, Hannah, that's awesome. So 2x minus 13x will give us a negative 11x. Perfect. Always be careful, keep the variable with your term. You're basically saying I have 2 x's and I want to take 13 x's away, which means, okay, now I'm in the whole 11 x's, right? Then we have a positive 3y and a negative y. So you're up 3y, you lose 1y. The 1 is in front here as our coefficient. So negative 1 is our coefficient of this term. 3y take away y is a positive 2y. And lastly, we have a negative 7 and a positive 11. So negative 7 plus 11 is going to give us a positive 4. If there are any questions as we go through this, please don't hesitate to write that in the chat. Let's take a look at number 2. What operations do you see for number 2? And then what I'd like you to do is just take a couple minutes, distribute and combine like terms. Let's take a couple minutes starting now. Okay, so let's take a look at this. So within the chat box, I'm noticing that you're recommending that we write down that we are using addition and multiplication, which I'm totally down with. That makes sense. We are going to distribute the negative 17. We're also going to distribute the positive 6. So hence we are definitely using multiplication. And we know the operation in between these two terms is addition. So we are going to distribute the negative 17 to each term. Let's start here first. Negative 17 times a positive 6m is a negative 102m. A negative 17 times a negative 2n is going to be a positive 34n. Be very careful with your signs as you distribute. Thank you. Thank you, Kayla, Rachel, and Maria. So now let's distribute the positive 6. So a positive 6 times a 3m is a positive 18m. And then a positive 6 times a 10n is a positive 60n. At this point, we're going to focus on combining like terms. So we have a negative 102m and a positive 18. So negative 102 plus 18 is going to give us a negative 84m. Next, we have a 34n positive and a 60n. So when we add these two together, that will give us a positive 94n. And that should be your final answer. Excellent work, everyone. Very, very nice. Let's take a look at number 3. Number 3 says 5 times 2/5 x minus 1/10 p plus 3. Just by reading the problem out loud, we know that the indicated operation is multiplication. That is the indicated operation. So what we're going to want to do is distribute the 5. Now please don't panic. I know some of you are still not totally comfortable with fractions, but you've got to get there, okay? I want you to think about the rules for multiplying. I want you to think about the rules for dividing, adding, subtracting fractions. So keep those rules in your mind as you work through all of these problems throughout the whole semester. So 5 times 2/5, keep in mind, and by the way, it's 5 times 2/5 x. We could do a little bit of side work if you want. That way it doesn't clutter up our space. So we have 5 times 2/5 x. Recall that every whole number can be written over a 1. So if we have 5 over 1 times 2/5 x, well, we always should try to reduce first. So we're going to reduce numerator for denominator. 5 into 5 once, 5 into 5 once. That leaves us with a 2 over 1x, or simply a 2x. And there's our first term. Next, I've got 5 times a negative 1/10 p. So 5 times negative 1/10 p. Again, place that whole number over a 1. And let's reduce. 5 and 10. I could say 5 goes into 5 once and 5 goes into 10 twice. Remember, we simply move from left to right when we multiply, so this becomes a negative 1 over 2p. So negative 1 over 2p. And that's my second term. And last but not least, 5 times 3, that gives us 15. We should always double check here. Notice that, wow, my camera's doing weird things. Okay, here we go. Notice that after we distributed, that my terms are not like. Nothing can be combined here. And that means we're done. So I want you all to try number 4. Number 4 says 7/9 times 8/14 x minus 2/7. Let's do this in 60 seconds starting now. Excellent. I'm loving what I'm seeing in the chat here. I'm also loving the fact that we recognize that we are multiplying, so I'm going to write multiplication. And we also realize that we are distributing that 7/9, so we have to be careful in our reduction of our fractions. So I'll show you. So we have 7/9 times 8/14. So 7/9 times 8/14 x. First things first, we can say 7 goes into 14. So 7 into itself once and into 14 twice. But notice here, 8 and 2 also reduces. Okay, so 2 goes into itself once and into 8 4 times. That leaves us with 4 over 9x. So if you had gotten 8 over 18 initially, that's okay. Just keep reducing as far as you possibly can. 8 over 18, both numbers are even, so they're both divisible by 2. Excellent. Then we have 7/9 times a negative 2/7. 7/9 times a negative 2/7. Notice here that my 7's, numerator and denominator, I'm going to divide them out, and that leaves us with 1's here, and we're left with a negative 2/9. So minus 2/9. If you had written plus a negative 2/9, that's totally fine. I would prefer that you did not use more than one sign in between terms. So if it's a plus, great. If it's a minus, great. Okay, so let's commit to one of those. Perfect. Try number 5. This one's tricky. You notice right off the bat that you have to multiply, but you should also notice another operation here. So be very careful as you distribute and as you combine like terms. So I'm going to give you about 2 minutes to play around with this. Let's see what you got. Okay, let's take a look at this more complicated problem. It's complicated because we are dealing with operations on fractions. So we just have to be careful. We'll just slow it down a little bit and make sure that we are applying the rules for operations on fractions correctly. So first, we notice that we are subtracting and we're multiplying, so hence the distribution. So I'm going to write here subtraction and multiplication. Okay, so those are the two operations that I'm focused on. Next, I recognize I'm going to distribute the 3/11ths to the first two terms, and then I'm going to distribute the negative 2/3 to the second two terms, right? Within the sets of parentheses, of course. So 3/11ths times 5x is going to give me 15/11ths x. If that was weird, remember, always write it out on the side if you need to. So 3/11ths times 5x. Nothing reduces here, so we multiply straight across. 3 times 5x, 11 times 1, or 3 times 5, 11 times 1. So 15/11x. There's a first term. Next, 3/11 times a negative 1. Well, when you multiply by a 1, that is an identity. So 1 times anything is anything. For instance, 7 times 1 is 7. 3 times 1, 3. 3/11 times negative 1, negative 3/11. Yeah, Kevin, this is definitely a tricky problem, but it's okay. And as with more practice, it's going to get easier and easier. Next, we have a negative 2/3 times 9x. Let's do a little bit of side work again. Negative 2/3 times 9x. We'll put the 9 over a 1. Notice right away that I can reduce the 3 and the 9. So 3 divides into itself once and into 9 3 times. So I'm left with the negative 6 over 1, which is just negative 6x. Perfect. And lastly, I have negative 2/3 times 12. Again, if you'd like, write it out. Negative 2/3 times 12. 3 goes into itself once and into 12 4 times. And that leaves me with a negative 8. If you had this part, this line, that is fantastic. That means you're very comfortable with multiplying by fractions. And that's awesome. You want that to be the case. But now we have to focus on combining like terms. So right away, we notice that 15/11ths x and negative 6x, these are actually like terms. Because we are adding or subtracting fractions, we need a common denominator. So if we wanted to, again, I could do some side work. So 15/11x minus 6/1x. If I'm adding or subtracting fractions, I need an LCD. We know that my LCD for these two terms is 11. So I'm going to multiply this second term, numerator and denominator, by 11. That gives me 15/11x minus 66/11x. So once we have 15/11ths minus 66/11ths, that will leave us with negative 51/11ths. So when we combine these two terms, that leaves us with negative 51/11ths x. As always, try to reduce that whenever possible. Next, we have negative 3/11 minus 8. These are both constants. So we're definitely going to combine these two. So negative 3/11 minus 8. Put that 8 over a 1. Same idea. What's my LCD in this case? Oh, my LCD is 11. So I'm going to multiply the denominator and numerator by 11. So now I have negative 3/11 minus 88 over 11. And when you take a negative 3 and you subtract 88, that leaves you with negative 91 over 11. So minus 91 over 11. That looked pretty crazy, and it was intense because there were so many different moving parts. We had to be careful with distributing our fractions, and we did exactly that. So this one was not too terrible. But then afterwards, we had to focus on adding or subtracting like terms. And I think that's the tricky part here, is being very careful with all of your signs, making sure you have a common denominator, etc., etc. What are your questions for me on problem number 5? Oh, Claire, that is an excellent question. You will know that you need to have a common denominator when you add or subtract fractions. Ah, Hannah, I totally get that. These look like they're not like terms because we have a fraction coefficient and an integer coefficient, but that's okay. Both of these terms have the x variable, so these will be combined, and then these two are constants, so those will be combined. So be super careful as you move through these types of problems, especially in your homework in Lumen. Okay, so let's take a look at this next section. So I have a quick note for you all on fractions raised to a power. Notice it says 3/5 to the third power. Whenever you raise a base to a power, you essentially take that base and you multiply it by itself, by the number of times that is represented in the power. Wow, I said that really weird, but here's what I mean. 3/5 to the third is simply 3/5 times 3/5 times 3/5, right? There's 3 factors of 3/5. So 3/5 times 3/5 times 3/5, that's the same as 3/5 to the third power. And Ria, that's okay. I wanted for you all to have a problem that was as complicated as number 5 so that you can use all of the operations on fractions. So that's just going to take some practice. Going back to fractions raised to a power, 3/5 to the third power, notice we cannot reduce anything numerator for denominator, so we're simply going to go straight across. Remember, that's how you would apply a power to a fraction. So 3 times 3 times 3, that's going to give us 27, right? 3 times 3 is 9, times 3 is 27, and then 5 times 5 is 25, times 5 is 125. So just so you know exactly how to apply it. Rachel, that's excellent work. Let's get into solving linear equations. This is the part where I'm going to show you so many different techniques that you may be kind of frustrated with that and wondering, you know, which rule can I use? Like, what technique do I use where and how and who? And the moral of this story is that I want to give you as many tools as possible. I want to show you all the things you can do with the math that we're learning so that you can develop your own style. You probably, you might do things just like I do, you might not. But I want you to develop your own style grounded in the theory, grounded in the rules. What am I allowed to do? So I think having that understanding gives you a lot of power, because it gives you the flexibility to try different things on these particular equations that we're going to be looking at. Make sure that you kind of categorize in your mind what those rules are and you're applying them carefully so that you're not breaking any of those rules. Okay? All right. So first off, Hannah, you can definitely do that on a calculator as well with the 3/5 raised to the third power. And you can do that. Let me show you really quickly so you can see it. If we had, so for instance, let's use parentheses to show that it's a fraction, the entire fraction raised to a power. So parentheses 3 ABC 5, see how it's 3/5. So 3/5 raised to the, notice this caret raised to the third power. It's called a caret. So raised to the third power, and there we have 27 over 125. So it does definitely do it for you, and that's why I really like the TI-30X2S. Okay, solving linear equations. First bullet, only solve for a variable if you are given an equation. You might think that's crazy, but you don't know how many times I've seen students solve an expression. Literally solving an expression that did not have an equals. So you have to be careful. If it doesn't have an equals, it's an expression. If it has an equals, you're going to solve, okay? You're going to try to solve for something, for that variable, for the indicated variable, okay? A linear equation in one variable is written in the form ax plus b is equal to c, where a, b, and c are real numbers and x is not equal to 0. When you hear the phrase linear equation, I want you to see the root word here, which is line, okay? So essentially, what we're doing is we're laying the foundation to eventually graph lines, but we'll get there. So anyways, are the following equations linear? How do you know? Okay, so let's also describe for a moment that we know an equation, I'm going to abbreviate, hope you don't mind. We know an equation is linear if the variables are raised to a power of 1 and no higher. Okay. Your equation is linear if the power of your variables is 1. So for instance, let's take a look at number 1. Are the following equations linear? How do you know? For number 1, we have 5x plus 9 is equal to negative 17. Notice here I have 1, 2, 3 terms. My first term is a 5x, my second term is a positive 9, my third term is a negative 17. Notice here my variable of x is being raised to the power of 1. When you don't see the power, it should be automatically assumed to be 1. So because this is 5x to the first power, this is linear. So yes, x is raised to the first power. That's how we know. X is being raised to the first power. If we look at number 2, we have 3x minus 1/4 y is equal to 0. Is this equation linear? Well, again, same idea. Notice we have 1, 2, 3 terms. 2 of these terms have variables, and they're actually both being raised to the first power. This is 3x to the first. This is negative 1/4 y to the first. So yes, even though we have 2 different variables, they're in separate terms, and they're both being raised to the first power. So yes, both variables raised to the first power. Okay, and last one for the day. Number 3, 14x squared minus 8x equals 2. Notice here, we still have 3 terms, but automatically you see, whoa, wait a second, 14x to the second power? Okay, because our power is greater than 1, this is no longer linear. So no, our x term is being raised to the second power. Okay, I know you see here a linear term, so you're thinking, but wait, what about that guy? Well, negative 8x is a linear term, but 14x squared is a quadratic term. So the entire equation becomes quadratic because of the highest power you see here. So this equation is actually quadratic. It's no longer linear. All right, excellent work today. Again, I kept you an extra minute. I'm so sorry. Continue to work through this material in your Lumen, and as always, if you have any questions, don't hesitate to ask. We will pick up where we left off tomorrow by solving linear equations, so be prepared, okay? Be prepared, open your minds, we'll have a great class. All right, everyone, enjoy the rest of your day, and I'll see you tomorrow.